Good morning, I'm Tim Pettersen, developer provocateur at Atlassian. Welcome to the Ultimate Git Workflow Software as a Service edition. Now you're definitely listening to the right webinar if you're currently using a version control system that isn't Git, but you're thinking about migrating over, or if you're already using Git, but you don't feel like you have a perfect workflow for your software team. Or you're in the right place if you just like talks about Git and workflows. Though the focus of this talk is software as a service, most of the talk applies to general development workflows, so you don't have to be a SaaS developer to get something out of it. Now, why am I here talking about Git? Because I'm one of the two developers who started Stash at Atlassian. So I spent a good 2 years of my life as a core developer on our Git hosting product, and another 18 months speaking and blogging about Git and Git workflows. I won't be talking too much about Stash during this session, but feel free to ask me about it in the questions. Now, there are 4 different sections I want to cover today. First of all, I'll be talking a little bit about why developers everywhere are falling in love with Git. Then I'll talk about the ultimate branching, merging, and rebase workflow we have for developing SaaS applications at Atlassian. Then I'll talk a little bit about speeding up your development by applying continuous integration to Git branches. And then finally, we'll discuss the finer points of pull requests and why they're important for your workflow. So first of all, why should we be using Git in the first place? Well, Git is the version control sensation that's sweeping the nation and the world. Developers love it for its speed, the fact that it can be used offline, and the fact that it has a huge number of great collaboration features that make it easy to be used in a distributed team. Plus, it's created by Linus Torvalds, the guy who gave us Linux, which gives it a huge amount of geek credibility. And there's a certain peer pressure aspect to switching to Git as well. When you look at the statistics, you can see a huge swing towards Git across the industry. So here you can see 37% of development teams are currently using Git, with only 48% on the traditional centralized version control system Subversion and 9% remaining on CVS, a version control system so old that I had to steal the CVS pharmacy logo for it because I couldn't find a PNG of the current CVS logo online. And for you Mercurial developers out there, while Mercurial is a pretty great version control system in its own right, there is a fairly alarming statistic when it comes to Mercurial adoption. Only 2% of teams, that's 1 in 50, are currently using Mercurial. And this has led to a whole bunch of factors, like Git being the tool that is taught in universities, and the tool that is generally being adopted across enterprise software development houses. So if you are tossing up between switching to Git or switching to Mercurial as your DVCS of choice, I'd strongly recommend using Git, because that's the version control that most developers out there are going to have experience with and will choose as a preference. And when you look at the VCS trends since 2010, you can see that that swing is even more pronounced, with plus 27% of teams switching to Git, and only plus 0.75% switching to Mercurial. And you can see, of course, a downward swing for both CVS and Subversion being the traditional centralized version control systems. And it's not just trendy small development shops and open source projects using Git. Here's a list of some of the enterprise customers that are using Atlassian Stash to host their Git repositories. Now, I'm not using this slide as kind of a sales pitch for Stash, but more just an example of the size and scope of organizations that are using Git for version control. These aren't small 1 or 2 person development shops. These are gigantic enterprises using Git to collaborate effectively on the software they develop. Now, I mentioned before that Git was built by Linus Torvalds. Actually, truth be told, Linus has pretty much signed off on the Git project for the moment, but he has left it in the capable hands of the Linux kernel and file system developers. So Git is written almost entirely in C with a bit of scripting as well. And basically this means that it is incredibly fast and is maintained by an exceptional crew of kernel hackers. So with both Bitbucket and Stash, we have attempted on occasion to rewrite certain aspects of Git's internals, but to be honest, we've never come close to the raw performance that is provided by using native Git. And I just want to take a moment to dispel a popular myth about Git, and that is that it doesn't handle large repositories. Now, this is patently untrue. If you look at the Linux kernel 3.1.3, it has over 15 million lines of code. of which 12,000 of the commits in its history are non-merge commits, containing actual content. And just that 3.1.3 release, over 446,000 lines of code were added by 1,339 different contributors. So basically, in summary, if your repository is smaller than the Linux kernel, and it most likely is, you're going to have absolutely no problems migrating to Git. That said, there are a couple of idiosyncrasies involved in switching to Git, particularly if your repository contains very large binary files. Fortunately, my colleague Nicola Bellucci has put together a great blog about handling big repositories and repositories with large files in it with Git, and you can check that out on the URL below. Now, I mentioned before that one of the big reasons why developers love Git is the fact that it's incredibly fast. And this is actually tied to that other very attractive quality of being able to work offline. Now, if you look at this set of, well, probably fairly unscientific charts, you can see that the speed of Git operations far outpaces every single one of Subversion, except for the initial clone of the repository. Now, this is because when you do a clone of a Git repository, you actually get the full history of it locally on your disk. So this means that every other operation you perform on that repository doesn't involve a network call. In fact, it can do all of the calculations it needs to do commits, browse through the log, or even run expensive operations like blames without having to call out to your Git server. And this, in essence, is what makes Git so fast. And just to throw up some other statistics which take a slightly different slant on Git, here's some survey results that we got from a couple of large Java conferences that we attended last year. And what we're plotting here is the frequency of release for developers using Git versus the frequency of release for developers using centralized version control systems like Subversion and CVS. And now what's really interesting to see here is that there's a large contingent of developers using Git that actually release their software daily. Now, I strongly suspect that these teams are developing SaaS applications, where performing a release really just involves deploying to your production server. And it's interesting to see how compelling it is, and it's interesting to see how many of these teams have chosen Git over centralized version control to ship their software. What we'll be digging into as part of the rest of this presentation is the reasons as to why these SaaS teams are preferring to use Git. Now, I did mention in the notes for this presentation that I'd be including some tutorials on how to migrate to Git. I've actually decided to remove a lot of that content because we actually have a full set of documentation, tips, and tools for performing that migration at our Git microsite at atlassian.com/git. Now, the reason that I decided to remove it was because we have this rich set of documentation, but also because during part of our research leading up to this, we determined that most teams out there are already using Git. And what was more needed was some guidance on how to set up that perfect Git workflow rather than the actual initial migration. But if you are still on Subversion or CVS, please immediately go to atlassian.com/git and check out our migration guide to help you out. Now let's dig into the nitty-gritty of building a workflow on top of that. And when I say the ultimate workflow, this is going to be the ultimate branching workflow for Git. So at Atlassian, we're big believers in using branching for enterprise software development over some of the other popular forking-based workflows. We believe that forking is very useful for open source, but when you're working with a tight-knit group of developers or a set of developers working for the same organization, we've found that branching involves less configuration overhead and a much more convenient way to develop software. So that's why we're sticking with branching for this presentation. There will be a little bit of a discussion on how to use forks for collaboration at the very end. So a good workflow should be able to direct a team of software developers on how to create and maintain a code base. But a great workflow should let you answer certain important questions about your code base at any point in time. These can be questions like, hey, if I find a bug before we release our software, how do I fix it and where do I commit that code to make sure that it gets released? And if I'm looking at a feature branch, how can I tell if that code is feature complete, or whether there's still some work to be done by the developer who's currently maintaining it? Or in the worst case, where we discover that there's a bug that's being shipped to our customers, how do we hotfix that and deploy it to our SaaS application as quickly as possible? And finally, if we're using code review, and we really should be using code review, how can I tell if everyone has reviewed the code and it's feature complete and ready to ship to our customers? Now, I know I called this presentation the ultimate Git workflow, and I'd love to be able to point to a diagram and say, hey, this is how you should be developing software. Unfortunately, the picture is a little bit fuzzier than that. Every single team has a different set of requirements for their workflow. What I can do, however, is show you some of the base requirements that all of the SaaS workflows we have at Atlassian have for software development. And hopefully you can use those pieces of information and design a workflow that will work for your team. So there are several factors that contribute to designing a workflow. The first is considering the culture of your company. If you're a Silicon Valley startup that's selling designer pet food to residents of the Bay Area, then the repercussions for shipping a bug to those customers might be a little different to if you were working on a large open source security project like OpenSSL, or working on the security layer for a Bitcoin exchange, for example. Similarly, different types of product have different workflows as well. Now, if you're running a SaaS application where the only version of your software is running on a server that you control, then you can immediately deploy a bug fix to that server without having to go through the rigmarole of a large release and distributing all of this software out to your customers. But if you offer an enterprise version of your SaaS application where large companies can download and install it on-premise, then your workflow is going to be slightly more complicated because you're going to have to maintain separate stable release versions of that product so that you can do things like backport bug fixes. So in the case of a security event, you don't have to get all of your customers to upgrade to this latest version. Instead, they can just apply a patch or upgrade to a minor or patch release version of your product. So the type of product that you're working on has a big influence on the type of workflow that you use. Similarly, different teams have different Git workflows as well. Now, if you're working on a 1 or 2 person team where you're sitting right next to the other developer and maybe doing a lot of pair programming, you may not need a super formal workflow because you both have a lot of control and a lot of insight into the code that's being developed. But if you're working on a large team, or perhaps working as one of several teams developing on the same product, or maybe working with open source or contract developers, then you're going to have a more formal workflow so you can prescribe how all of these different parties can contribute to your code base. So what I'm really saying here is that there's a whole bunch of different factors that contribute to the type of workflow that you're going to use to develop your software. So let's take a little look at the fundamentals of the workflows that we use at Atlassian. So there are kind of 2 different components to every software project. There's a set of issues that need to be implemented. So these are the business problems that are going to be solved by the code that you're writing. And then there's the code that implements these issues. So these are the deltas, the diffs, the patches, the actual lines of code that are being written by your developers to solve those business problems. Now, if you're using Atlassian Jira for issue tracking, each one of those issues is going to have a unique key. And there's been kind of a common pattern when it comes to Subversion or other non-branching development workflows, where each one of your commits should have a reference to the issue that it's fixing. Now, in traditional linear development, and I'm going to use the term linear here to denote a non-branching workflow, sometimes it can be a little bit hard to tell what state your code is in, because all of your developers are incrementally committing to the same branch. So you can get this issue known as commit interleaving, where you have some work relating to one issue, a commit relating to one issue being committed to that main branch, then a couple of commits relating to another issue, and then a commit relating to that first issue again. So it can be quite hard to tell where one feature begins and another feature ends. Another problem of having this linear-based approach to development is that if someone creates a bad commit that breaks the build, it's going to affect everybody on the team. Now, this is stressful and embarrassing for the developer who created that commit because you have this huge audience watching you try to fix something as quickly as you can. In fact, when I last worked on a Subversion-based product, I was helping maintain Atlassian's Fisheye and Crucible project, and that was, about 4 years ago now. And we were using Subversion at the time. And we actually had this red fire warden's hat that you had to wear until you fixed the build. And there's nothing more depressing than sitting there at 7 p.m. on a Friday night wearing a fire warden's cap, trying to fix the code base so you can go home for the weekend. Basically, another pattern that emerged from having this broken build problem was something known as the code freeze. Basically, breaking the build meant that everybody else's development had to stop until you managed to fix it, which effectively means that development work is frozen and it causes the entire team's productivity to drop. Now, another problem with this kind of commit interleaving non-branching workflow is that you end up with these half-baked features sitting around on your trunk branch. Now, this means that it can be very hard to tell whether a particular feature is finished and whether it's ready to be released. So again, back on the Fisheye team, this meant that when we decided we wanted to release our software, we had to appoint one of our senior developers to be a release manager for a few days. And they'd have to basically go around to every single developer, tap them on the shoulder, and see if they had committed everything that they wanted to get into the release to the trunk branch. So what this effectively meant is that we'd go into another code freeze whenever we wanted to release our software. Because all of those developers who had finished all of their work for the release weren't allowed to commit to trunk until that release had been finalized. So there's got to be a better way to do development than this kind of linear trunk-based workflow. Fortunately, branching in Git solves both of these problems really nicely. Now, what a branching workflow means is that for every single code change that you make, whether that's a feature or a bug fix or a tiny improvement to the documentation, you create a new feature branch for it. Then you get all of the work on that branch complete before you merge it back in. So that means that the integration tests are passing, it's being code reviewed, and you have no more intended work to be done on that feature before it gets shipped to your customers. And then you merge it in. So this has two really nice features. The first is that you have isolated feature work on that branch. So this means that if someone else breaks the build on another branch, you don't care because you're working in isolation and you can continue committing to that branch and pushing to the server until you're ready to release. And the corollary of this is that you have a stable master branch that always has green builds from your continuous integration tests and that only contains releasable features that are completely feature complete. Now, this is super important in a SaaS context because when something really scary happens, like shell shock occurs and you have to upgrade the version of Bash that you're running, or Heartbleed happens and you have to quickly patch OpenSSL, then you know that you can just check out your master branch, create a new hotfix branch, fix that problem, merge it back into master, and deploy it to your servers. Now, if you didn't have a stable master branch, then this would be a lot scarier because you'd have all of these half-baked features floating around on trunk or master, which would make it a lot harder to quickly turn around a critical bug fix when the shit hits the fan. Now, at Atlassian, we use a couple of different naming conventions for our branches. We prefix every branch with the type of issue that we're fixing on the branch. So this is feature for a new feature, or bug fix when we're fixing a bug that hasn't been released to customers yet, or hotfix when we're fixing a bug that is already out there in the wild and we need to turn it around as quickly as possible. Now, one of the important things about adopting feature branching is to make sure that you branch for every code change that you make to ensure that you always have this isolation on your feature branches and a stable master branch. So this means that you're branching for every feature, you're branching for every bug, you're branching for every minor change, even documentation changes. Basically, the thing to remember is that you should be branching all the things all the time. Unfortunately, Git's sophisticated branching and merging algorithms make this branching all the things workflow perfectly easy and straightforward to do. So we've discussed a couple of different reasons as to why branching is valuable for you and your software team. The first is isolation, in that all of your developers are insulated from build breakages caused by other people. The second is stability, in that you always have a stable master branch from which you can turn around a deployment very quickly. The third reason is traceability. Now that each branch in your repository contains a single feature, you can reason about what features are shipping in a release by determining which branches have been merged to master. So for example, if I wanted to see which features have been shipped as part of the 2.0 release in Stash, I could check out the 2.0 tag and run git branch -- merged to find a list of branches that have been merged into that tag. Similarly, if I'm a team lead or a product manager curious about what work is left to do for a release, I can run git branch -- no merged to find out what branches are yet to be merged into master. Now I'd like to quickly address a problem that's probably niggling at the back of some Subversion users' minds out there in the audience. And that is, why can't I implement the same branching workflow in Subversion? Now it's true, Subversion does support branching. And in fact, creating a branch in Subversion is pretty cheap and quick. However, what is not quick or cheap or particularly pleasant is performing a merge in Subversion. Now the guts of it is that merging in Subversion isn't quite as sophisticated as it is in Git. When you perform a merge in Subversion, it's typically considering every single change that occurred on that branch. Whereas in Git, it actually does a thing called a three-way merge, where it looks at the tip of both branches and then the common ancestor and computes the merge from there. So what this means is that in Git, you'll end up with less conflicts. The other thing about merging in Subversion is because you don't have the full history of your repository locally, it means that it has to call out over the network to retrieve the contents of that repository and perform the merge. This means that it's also a much slower process. So all of these factors kind of combine to mean that teams using Subversion typically don't branch for every single feature. Instead, they'll usually have a trunk-based or linear development flow. So I've kind of pitched the stable master branch and feature branching concept as the, solution to all of your development woes. But in the form that I originally showed you, it's not quite true. Although you do typically have a stable master branch when following a feature branching workflow, there is one situation where you'll run into problems, and that is where you have an integration failure. Now in this diagram here, imagine that we have two different changes that in isolation work correctly. But imagine that when combined, they cause an integration failure. So one common pattern where this may occur is where, say, we made a change to some internal REST API in Jira 123, and then we added a new feature in Jira 456 that depended on that REST API maintaining the same shape. Now, both of these sets of tests are going to pass in isolation, but when they're merged together, they're going to cause that to fail. Now, unfortunately, the place where this is going to fail is on your stable master branch. So it's now an unstable master branch, which is a problem for SaaS. So what we've done at Atlassian is introduced an intermediary branch where we merge features first, known as develop. So basically, develop is considered as unstable, and it's where we integrate all of our different features together, and then, if there are problems with the build, fix them before merging to master and deploying to our production servers. So this gives us this extra level of stability and insulation to prevent failures from making it to production. Now you can call these two branches whatever you want. It could be production and staging, like it is in our Bitbucket team, or deployment and integration, or Alice and Bob. Git doesn't really care what you name your branches. But for most teams, we typically call it master and develop, to follow on with the popular Git flow pattern of software development. The other cool thing about having these two separate branches is that if you have a staging server, you can continuously deploy green builds from your develop branch to staging, and continuously deploy merges to your master branch to production. Now, because master only ever has green builds from develop merged to it, you know that your master branch is completely stable. Now let's look at a slightly different workflow methodology that we can use to apply a critical patch to our production server. This is known as a hotfix. So we have our two branches, master and develop. Master is being continuously deployed to production, and develop is being continuously deployed to our staging server. Now imagine we're on the Bitbucket team on the day that the Heartbleed vulnerability is discovered in OpenSSL. What we'll want to do is upgrade the version of OpenSSL running in production as quickly as possible, but we do want to run a couple of tests first. So what we do is we create a new feature branch off of master with the hotfix prefix, since this is a hotfix. Then we upgrade the version of OpenSSL and make sure all of our unit and integration tests are passing. Then we want to do a little bit of testing against this against our live server. So we merge that branch into develop. This triggers a continuous deploy to staging, and all of our users can immediately test to see that OpenSSL is still working correctly in a staging environment. Now what we don't want to do at this point is merge develop into master. And this is because we have another bunch of unrelated features that have been sitting on develop, waiting to be pushed into production. And these may not be quite stable or ready for production because they're still being tested. So what we do instead is merge our hotfix branch back into master. This triggers a continuous deploy to production, and it means that Bitbucket is now protected with the latest version of OpenSSL. When we merge develop into master later on, Git will notice that the commit on the Jira 1911 branch has already been previously merged, and it won't reapply those changes. So this is essentially how we perform a hotfix, or a critical production fix, to our master branch and deploy it to production. So we've talked a lot about merging. Now let's look at a couple of the different merge strategies available to you in Git. First of all, let's discuss exactly what a merge is. Basically, a merge is Git creating a commit with two parents. This indicates that you've merged a feature branch back into your master branch.
Now, let's contrast that to what a rebase is. Rebasing can be a little hard to understand at first, and I'm going to try and explain it using a common scenario. Imagine you're working on a long-lived feature branch. It contains days or weeks worth of commits, but you're not ready to merge it back to master just yet, because it's not finished. In the meantime, development on master has also continued, and you want to use those changes on your feature branch. Maybe a bug has been fixed on master, and you need that fix for you to be able to progress your branch. So far we've talked about merging feature branches into the main branch, but our branch isn't finished yet. Now, instead, we can do the reverse. We can merge the main branch into our feature branch. Note that this does not affect the main branch. It stays exactly where it is. We just pull its changes into our branch, and this creates an automated merge commit on our branch, and so we can continue development. Now, after doing this a few times, we'll see a pattern of normal commits interleaved by merge commits. Now, this is no big deal, except that if we want to see everything we did on our branch since its creation, we'd see not only our own work, but also the changes that were pulled in from master. And this is work that is completely unrelated to our feature. Rebasing addresses this problem. Now imagine instead of merging master into our branch, we instead got all of the changes that we created on our feature branch and turned them into a series of patch files containing the exact changes that were associated with each commit and ordered by the timestamps in which those commits were created. Then we delete our branch and create a new branch off the tip of master. Then we sequentially apply each one of those patches in the order it was created. What we end up with is a series of commits on a branch rebased from the tip of master. And this is essentially what Git does when you rebase, except you don't have to manually extract and reapply all these patches. Git will actually do all of that for you in a single command and automates what would have otherwise been a huge amount of manual labor. You can also use rebase in the other direction and actually use rebase to apply the changes from your feature branch back to master without creating a merge commit. Basically, a rebase towards master does the same thing. It reapplies each commit in the order that was created on the feature branch onto your master branch. However, it's actually creating new commits, which is a point that I'll come back to in just a second. At Atlassian, we typically don't recommend doing the rebase back onto master. Although it is slightly cleaner because you don't create merge commits, it does mean that it's a little bit harder to reason about whether a feature was developed on a branch or whether it was developed directly on master. And it can be a little bit hard to see where one particular feature ends and another particular feature starts. So typically we recommend doing a full merge with a merge commit when you merge your changes back to master. If you're interested in learning a little bit more about the various ways you can rebase your branches, you should check out the -- interactive flag for use with a rebase command. It allows you to have full control over the way that your changes are reapplied to another branch. And you can do things like reword the commit messages of the changes that occurred. You can squash commits together or break them apart if it makes more logical sense to have a single change spread out over several commits, and even change the contents of the commits themselves. Now, there is one customary warning that I have to give for anyone attempting to rewrite history, which is pretty much what you're doing as part of a rebase, because you're actually creating new commits. The general rule of thumb is that you must never, ever rewrite history that's already been published to a common branch. Because if you do, and a developer pulls down your new commits, it won't realize that they're supposed to replace the older commits that they already have on that branch. So you should typically only rebase a branch that you haven't made public yet. Now, with that in mind, let's take a little look at the various workflows you can use for merging and rebasing branches. And I'll come to bring it all together with a summary of what we use at Atlassian. So the first strategy that we looked at was the simple, straightforward merge commit, which creates a commit with two parents, the tip of the feature branch being merged in and the tip of your master branch. The second option you have is a fast-forward rebase for merging your feature branch onto master. This basically means that you take all of the commits that you have in your feature branch, rebase them off the tip of master, and then fast-forward the master ref to point at the tip commit. So this is basically a vanilla flavored rebase that we just looked at. There is another variation of the rebase workflow called the squash. Now, this basically involves doing an interactive rebase of your feature branch and squashing all of your commits on that branch into a single commit that gets applied to the tip of master. Now, this is nice because it's quite a concise history, but you do lose a lot of the actual interstitial changes that occurred on that branch. And sometimes you might miss the subtle development of a bug that occurred during that feature's development. So when you're trying to pick a merging strategy or a rebasing strategy for your team, you should bear in mind these different facets of functionality. For the merge commit, if you decide to always use merge commits, you might end up with a bit of an ugly history because you do have all of these merge commits, which are really kind of metadata about your repository. They're not actual kind of content changes. They're just showing you where two different lines of history have converged and come together. Fortunately, merge commits do allow you to have full traceability of your repository, and you can see exactly which branches certain commits were developed on, so you can basically go back and trace through the evolution of your repository. Also, merge commits are the simplest workflow, and it's really hard to screw up and lose history if you stick to merge commits. Now, the fast-forward version of rebasing, where you basically apply your branch to the tip of master, does get rid of merge commits and does keep a reasonably verbose history because you can still see all of the original code changes that were authored by individual authors on their feature branches. However, we don't typically use rebasing to merge feature branches back into master at Atlassian because we lose that traceability. And finally, there's the rebasing with a squash interactive rebase that allows you to have a very minimalist history where each feature that was developed on a branch just takes up one commit. So this makes it a very pleasant history to read, but it can be a lot more difficult to trace changes because you're actually rewriting a lot of your repository's history at merge time, which can be a little bit problematic. But, again, it depends a little bit on your team and their Git expertise as to whether you might adopt a workflow like that. At Atlassian, We mostly use merge commits to merge feature branches in, but we do occasionally rebase the feature branches themselves when we need updates from master. So we'll rebase the feature branch so it appears that it was branched off master, but then we'll create an explicit merge commit to merge that set of changes back into master. And we think that this is a nice balance of clean history with the full traceability that you get from using explicit merges. So that's the general gist of the branching, merging, and rebasing strategies that we use here at Atlassian. So now I'm going to talk a little bit about how our continuous integration strategies have evolved since we've switched to Git. Now, we'd been using continuous integration for a long time, even when we were back on Subversion, and even to some extent when we were back using CVS in the very early days of Atlassian software. So the common wisdom with any sort of branching strategy with continuous integration is to always run continuous integration against your master branch and your develop branch. The develop branch, because you're basically asserting that all of your feature branches still pass the tests when they're merged together. And your master branch, because you want to be 100% certain that the code that you ship to your customers is passing the tests. But there is a bunch of powerful strategies you can use for continuous integration that go beyond this two-branch model. I'm a big fan of the online comic XKCD, and one of my favorites from quite a few years ago was this developer sword fighting comic, basically indicating that code compilation can sometimes take a considerable amount of time, and if a developer says that their code is compiling, it's probably okay for them to be slacking off. Now, this comic is number 303, and I think that they're over 1,000 now, and Randall publishes something like 3 times a week. So processing power and memory and the number of CPUs you had per mainboard was significantly lower back when this comic was first published. These days, compilation of most systems, unless you're working on a very, very large, computationally expensive piece of software, compilation doesn't typically take that long. However, there is sort of a modern equivalent to code compilation that does suck up a lot of developer time and resources. And this is running the tests. At Atlassian, we have over a dozen products, each of which has a huge number of different tests. We have functional tests, integration tests, database tests, unit tests, QUnit tests, all kinds of stuff designed to make sure that we don't ship regressions to our customers. Now, the thing about having all of these tests is that they take an extremely long time to run. We've actually recently broken up the stash build into 12 different separate jobs that can be run in parallel to shorten the overall time it takes to run those tests. However, it still takes a good 40 minutes for a build to complete, although we are working on it all the time. Now, fortunately, using Git, specifically Git branches with continuous integration, can lead to a very powerful strategy that will save your developers a huge amount of time. So kind of the common wisdom with building your code in continuous integration is to always build your master branch, as we discussed before. Now, fortunately, modern continuous integration servers, including our own Atlassian Bamboo, have the capability of detecting when you push a new branch to your repository, and then cloning the master branch's build configuration and running that build against the feature branch. What this means is that it's completely changed the way that I do development. Before, when I was developing just off trunk using Subversion, I'd be paranoid about breaking tests, because if I committed those changes and broke the build, I'd have to fix the build as quickly as I could. Now, with feature branching and continuous integration running on my feature branches, I can just simply push my changes as soon as I've finished development and wait for Bamboo to build those changes for me. Now, it doesn't matter if it's broken because I'm developing in isolation on my own branch, but I can also use this to determine exactly which tests I have broken. Because when the build completes, Bamboo will send me a nicely formatted email saying that I've broken 4 or 5 tests, and then I can go through and iteratively fix and test each of those locally on my machine. So before, where I had to tie up resources running tests on my machine locally, now I let all that happen on a VM somewhere in the cloud, and I get the results emailed to me. So basically what this means is when I do feature development, I'll kind of develop for a little while, push my feature branch, and then immediately switch context and start working on another feature, rather than being blocked by having to run the tests locally. Now, the only problem with this is that you end up with a huge number of builds being run in the cloud. At Atlassian, we have something like 300,000 builds being triggered every month, because we're basically triggering at least one new build every time a developer pushes changes. So if scaling up your CI infrastructure to this extent seems like a bit of a daunting task, you can actually configure Bamboo and other CI servers to manually trigger these branch builds. So what will happen is Bamboo will detect that you've pushed a new branch, set up a new plan, but leave it disabled until the developer is ready to run those tests. And so this dramatically cuts down on the number of builds that you end up running. That said, I'd say the automatically triggered version is far more preferable because it's a lot more convenient for your developer to be able to just push and then wait for that email to be sent out. Of course, it does mean increased infrastructure costs, but at the end of the day, the cost of commodity hardware to run these builds is probably a lot cheaper than paying additional developers, particularly when you can make these developers a lot more effective by allowing them to develop features in parallel. So this brings me to a little stash feature that I want to show you. Now this is sort of opening up a broader topic that isn't stash specific, but I just have to introduce the topic using stash. So if you're not a stash user at the moment, bear with me. So this is the create branch screen in stash. This might seem a little bit crazy to Git users out there who are used to doing development from their command line or using a GUI tool like SourceTree, where they're used to creating feature branches locally on the client. What this screen lets you do is actually create a new feature branch in the stash repository that's on a publicly shared server. Now, the reason I want to show you this screen is because there's a recent addition to it that's very useful and has saved me days of debugging time over the last year. And that's this little 64 by 64 pixel green tick. Basically what it's showing me is that the tip of the master branch, where I'm about to create a new feature branch from, is currently passing the tests. Now, this might not seem like a big deal, but let me show you a scenario where it can save you a huge amount of time. Now imagine we've adopted a feature branching workflow for our team, but then a senior developer comes along and decides that she's going to be a little bit too cool for school and is going to create a commit directly on the master branch. Let's say it's a tiny change to the database layer in Stash. Now, she's a senior developer, so she's pretty sure she's got all the edge cases figured out. Makes a quick change to the database layer, commits it, and bam, predictably, the database tests fail. She immediately sees the error that she's made and decides to create a new commit directly on master to fix those changes, and then, seeing that the build is passed, disappears. Now, to the untrained eye, this might look like an okay scenario. Sure, we ended up with one red build on master, but the developer quickly fixed it, and the continuous integration tests are now passing, so presumably our software is good to ship to our customers. And in most situations, this will be okay, although it is unfortunate to have that red build in your history. However, there's one very specific scenario where this can cause another developer a world of pain. Imagine that we had another developer who's not too cool for school and decides to do the right thing and create a feature branch. But this developer has the misfortune of basing their feature branch off that broken commit. Imagine they're making another change to Stash somewhere completely removed to the database, say something in the authentication layer. They're going to make their changes, push it to the server, and then, magically, a test relating to the database layer is going to fail. And this is going to be really confusing for them, because they haven't been anywhere near the database layer with their code changes. But that's not going to stop them from indulging in all sorts of paranoid fantasies about how they could have possibly broken those tests. They're going to go through and put all sorts of ridiculous log statements in the code, step through it in the debugger a million times, and only eventually are they going to go back through their master branch's build history and realize that the build was broken before they even created their branch. I've been in this situation before, and the fact that I have this little green tick telling me that the master branch is green before I've created the branch gives me a whole bunch more confidence when it comes to branching. Now, as I mentioned before, this is a Stash-specific feature, but I have written a similar post-checkout hook that you can use on any Git repository. And this actually runs on the client side. All you need to do is clone the hook into your Git hooks directory, give it the configuration information for your CI server, and then it'll automatically tell you every time you check out a branch whether it has a current passing build or not. Okay, so now we've covered branching workflows and continuous integration strategies. Now let's talk about how pull requests can magically improve the quality of your code. So when we talk about quality in terms of software, what do we really mean? We're not talking about a fluffy Australian marsupial drinking boiled leaves. We're really talking about quality code. That is, code with low bugs, code that performs well, code that has a low level of technical debt, and code that's relatively easy to maintain. Now, there's a wide range of tools you can employ to help ensure the quality of your code. There's a vast array of testing techniques, from unit tests to front-end tests to functional tests and WebDriver tests. There's a huge number of different static analysis tools you can use, like checkstyle and lint. And you can even use things like code coverage reports to determine that you're writing the right kind of tests that cover all of the different branches in your code. But I think the most important tool you can implement to ensure the quality of your code is code review. And I've used this picture of a baby crying in the bath because getting a developer to do code review sometimes has a bit of a similar effect, at least the first couple of times. There might be tears, but code review, like baths, is good for the general hygiene of the developer and the rest of the development team. And just like a baby in a bath, after they've done it a few times, they might just start to like it. Now I'm going to call back to that survey that we looked at before, this time comparing the release speed of teams that use code review versus teams that do no code review. Now what's interesting to see here is that there's a strong correlation between teams using code review and faster release cycles. So you can see here that 11% of teams doing code review actually release software daily. And I suspect again that this is teams who are running a SaaS service and need to maintain a high level of quality in their code to ensure that they're able to release their code every single day. Now, this is an important and somewhat counterintuitive point, because as we know, code review does take a non-zero amount of time, and yet these teams that need to release extremely quickly, that is, every day, still take the time to do it. Now let's take a little look as to why they might decide that code review is valuable to their process. Now, there's kind of three key reasons why I think code review is important. The first is that you get better code. Now, this is kind of obvious, and it's basically just because having different developers with different levels of experience, different knowledge about different libraries and frameworks, and different specializations like security or front-end means that you're more likely to catch a regression or poorly architected code simply by having different people looking at it. The second important reason to do code review is this concept of shared knowledge. Now, this is a little bit more subtle, but still an extremely valuable reason to do code review. Now, back when I was on Crucible, which actually happens to be a code review tool, we were very heavily dogfooding our product and basically doing code review for every single code change that was made. Although at the time, we were still working on a kind of trunk-based development model because we were using Subversion. Now, what code review meant was that I got to see all sorts of changes that were being made by senior developers on my team. And this was a great learning experience for me as a relatively junior developer, because I could see the kinds of patterns that senior devs were using to solve problems that were common to my code base. The other cool thing about seeing other developers building new features and fixing bugs in Crucible is I got to see a lot more of the stack that was specific to this particular project. And this is really useful because every single piece of software out there has a different stack or a different set of libraries associated with it. And the only way to gain expertise with those libraries is to use them or to read code that uses them. So short of sitting there and reading through a code base which was a few 100,000 lines long, the most effective way for me to learn about all these different bits and pieces of Crucible was to go and see the changes that other developers were making to it. And code review is a really nice way of facilitating that. Now, the final reason why code review is super important is this concept of team ownership. So let me just ask all the developers out there in the audience, and think very carefully about this. have you ever shipped a bug to a customer before? Hopefully, and I'm pretty sure, well, not hopefully, but I'm pretty sure everyone is thinking, yes, I have shipped a bug. It's kind of a fact of life when it comes to software development. No matter how good your regression tests are, no matter how good your static analysis tools are, and no matter how good your code review process is, there is still some scope to accidentally ship a regression or bug to your customers. So it happens. But it's terrible. It always starts kind of the same way at Atlassian. You'll be sitting in a triage meeting, going through the issues that have come into Jira overnight. Your PM will be running the show and going down through the list of issues, and then suddenly you'll see an issue that has this summary that seems strangely familiar. And you get this sinking feeling. When it hits the top of the list and they click through and read through the description, your heart sinks because you realize that it is completely your fault. It's an edge case you didn't consider, or a unit test that you didn't write, and a customer on the other side of the world, probably multiple of them, is in a world of pain because of something you did. And I've realized there's actually a formula for this feeling of guilt. The level of guilt that you feel for a bug that you ship is equal to 1 over the number of people who reviewed that code plus 1. So if you're not doing code review, then you basically feel full guilt whenever you ship a bug to your customers. Now, I am somewhat kidding. Despite the fact that code review does somewhat reduce the guilt because it becomes a team responsibility, there's actually a very practical reason to do code review from a business sense as well. Now imagine that bug comes in, but I'm not in the meeting for some reason. Perhaps I'm on holiday somewhere, or I'm off sick, or I might have even left the company. Regardless, I'm indisposed. If I'm not using code review, then someone else is going to have to go in and investigate that bug and trace it all the way through to try and figure out exactly what the problem is. And then they're going to have to fix it. And they're effectively going in cold because they have no knowledge of what could have possibly caused this problem. However, if we're doing code review and there's 2 other reviewers who have signed off on it, then there's 2 other people who are ready and hot to go in and fix that bug straight away. And the turnaround is going to be much quicker. And the experience for the product manager running the session and the customers affected by the bug is going to be much more pleasant. And I think this is a quite often overlooked reason why code review is super valuable for your team. When we're talking about code review in terms of Git, we're really talking about a tool known as a pull request. So a pull request is called a pull request because you're basically asking developers on your team to pull your changes into the master branch. And what you're going to do is review those changes before you merge them. So there are many different Git hosting solutions, all of which implement pull requests. I happen to think that Stash has the best enterprise pull request solution out there. I'm happy to follow that up in the questions if you have questions about that. But basically what it involves is reviewing the diffs that occurred on your branch. Now, one of the kind of common the common bits of feedback that I get about code review and continuous integration is that they overlap. Sometimes people think that they don't need code review if they have a full set of continuous integration tests. Now, while there is some overlap there, they both do have to do with the quality of your code. They're actually orthogonal and they serve different and very important purposes. And let me illustrate that with another example. So one of the reasons why Stash pull requests are so neat is that they can actually prevent you from merging a pull request until it has a passing build. You literally can't press the merge button and it'll say, hey, you need a passing build. So Stash acts as this kind of robotic enforcer, preventing you from merging bad changes into master. So this is great as far as it goes. But there are certain things that continuous integration tests can't catch. Imagine we have a set of build results on a particular feature branch, and they're all green. From Stash's perspective, if you're just relying on continuous integration, it's fine to merge this branch because all your tests are passing. But if we look a little bit closer at these changes, there may be some undesirable things in there. For example, that first commit could contain crippling technical debt. Maybe it's a whole bunch of copy-paste code, or maybe it's a really bad architectural decision that's going to make feature development really painful for other developers in the future. Regardless, that's something that a continuous integration server isn't going to be able to pick up, because while it's logically correct and all of your tests are passing, that build is going to continue passing, even if there's undesirable stuff in that particular commit. Or what if a commit contained a horrible performance regression? Now, you can sometimes write performance tests that will fail a build if there's a certain level of performance regression, but they can be pretty finicky to write because it involves all sorts of baselining, and there are legitimate reasons why performance might slow down on a branch where it isn't necessarily a problem. For example, if you're doing some actual valuable work that the customer needs, you can expect that that's going to take some additional CPU cycles and potentially slow down the request. However, there is another class of performance regressions where you seriously shouldn't expect a regression, like upgrading a dependent library or making some cosmetic changes or restructuring an algorithm where you're actually expecting a performance increase. And these things are not going to be able to be picked up by a continuous integration server. Or what if that third commit contains a bad API decision? Now, a bad API decision is kind of like technical debt, but orders of magnitude worse, because it affects your customers as well. Basically, anyone who is depending on your API, whether it's a REST API or a Java API, is going to want a nice clean API to develop their integrations with. But if you make a poor decision when designing that API, you can't even fix it in the next release. You're going to have to wait until the next major release of your software to deprecate that and then eventually remove it. So unlike technical debt, which can potentially be fixed, like on another feature branch, a bad API decision, once it's shipped to your customers, can't be easily reverted. And in all of these situations, Stash is just going to say, whatever, you can merge that because you've got continuous integration builds that are passing. And this is why it's important to institute required reviewers for each of your reviews, to apply that extra level of human judgment that you get when performing a pull request. And the reason why I think Stash kind of has the best pull request implementation out there is you can actually enforce all of this stuff. You can say exactly how many people need to explicitly approve a review. You can make sure that they're unapproved automatically if the developer who authored the branch changes that branch underneath them. And you can also require that there's a minimum number of successful builds before that branch can be merged. The reason we have a number there is because, as I mentioned before, on the Stash team, sometimes you have more than one build building the same branch for performance reasons. So by using these different settings to enforce your pull requests, you end up with this nice balance of both robotic enforcer, ensuring that your tests are passing, and human judgment, ensuring that the code that was written on that branch is actually good enough to ship to your customers.